Hello and welcome to the talk named The Hidden Performance Price of Virtual Functions. So, a short introduction. My name is Ivica Bogosavljevic. I'm an application performance specialist. What does this means is that I'm an engineer who help make software run faster. My professional focus is C and C++ application performance, and these are obtained by several ways: by using better algorithms, by better exploiting the underlying hardware, better using of the standard library, programming language, and the operating system. I also work as an external expert, so if you have software and your software is slow and you need help, you can contact me and I can help you. I also write for software performance blog called Johnny Software Lab, and the link is in the footer. So if you're interested in software performance, visit this page to learn more about software performance. So let's start. First, a short introduction. So about virtual functions in C++. I assume that everybody knows what virtual functions in C++ are. They enable flexibility and they're a basic component of object-oriented programming. So you cannot imagine object-oriented programming without virtual functions, and the flexibility of modern software development is unobtainable without virtual functions. Now the problem is that virtual functions are slower than regular functions. Now, what does this mean, and why are they slower, and how are they slower, and under which conditions are they slower? So this is not an easy. There is no easy answer to this question. And in this presentation, we will talk about the reasons why they are slow, and also explain ways how you can mitigate the problems with their performance. So before we can dive deeper into virtual function performance, we need to understand how virtual functions actually work under the hood. So the C++ standard does not mandate how virtual functions are implemented. So the compilers can implement virtual functions in any way they like. But most compilers implement virtual functions in a similar manner, so let's present that. So here we see an example of array of instrument pointers. So we have a base class instrument, and we have 4 derived classes called wind, percussion, string, and brass. Now, each of these objects, for each type there, so not instance, but for each type, so for type wind, for type percussion, for type string, and for type brass, there is a virtual table. So virtual table has entries which are pointed to the functions that implement the corresponding behavior. For example, if you look at this example here, you see that the wind object for play uses wind.play. For a watt uses wind.watt. For adjust uses wind.adjust. And for example, the brass object for play uses brass.play. For watt uses brass.watt. But for adjust uses wind.adjust. So this is virtual pointer table is simply a table attached to each type. We know that for this virtual table, we know that the entry 0 points to the play method, entry 1 points to the watt method, and entry 2 points to the adjust method. So this is what the compiler knows already at compile time. Now at runtime, inside each instance, there is a pointer called with PTR, which is hidden, so you don't see it if you don't see it in GDB, but it's hidden, and it influences the class size. So there is this pointer which points to the corresponding virtual table. So if the object is wind, the virtual table will point to the wind virtual table, and if the object is brass, the virtual point will point at the brass virtual table. Now, when the object is constructed, this virtual pointer member of the class is set to point to the corresponding to the corresponding virtual table. Okay, now how does a virtual function call works? Well, if we are accessing an object through a pointer or through a reference, so what happens is that the compiler is accessing the virtual pointer, which is hidden, and then, for example, it wants to call the adjustment method of the brass object. The compiler knows that the adjust method is in the entry number 2 in the virtual table. So this is the entry number 2 of the virtual table. So it will reference this pointer, and it will get an address, and then it will go to offset 2, and it will read the address of the function. So this is the address of the function, and then it will call the virtual function. It will call the function with this address and in this entry. Okay, so this is how the virtual function mechanism actually works. So what is the initial analysis? Well, when you look at it like this, so we know how it works. Virtual functions are by their nature more expensive than non-virtual functions. Why? Because the virtual function address is not known at compile time. So the CPU has to look up virtual function address for each object, and this needs to be done at runtime, and when it's done at runtime, it consumes time. So what the runtime does is that it accesses the virtual pointer, and then it references the virtual pointer, and then it accesses the corresponding entry in the virtual table to get the address of the virtual function, and then it calls the virtual functions. You don't get this overhead with non-virtual function. With non-virtual function, the address of the non-virtual function is known at the compile time. So we did here one experiment. We have a vector of 20 million objects of the same type. And now we measure 20 million calls to the virtual function versus 20 million calls to the non-virtual function. We have two functions. So the function bodies are essentially the same for virtual and non-virtual functions. So they don't influence the runtime. We see here if the function is short and fast, the virtual function call takes 153 milliseconds, and the non-virtual function call takes 126 milliseconds. So for the short virtual function, there is some overhead, which is here about 20%. For a long and slow function, call to a virtual function takes 32.09 seconds, and call to the non-virtual function takes 31.84 seconds. So in case of the long and slow function, there is almost no difference between call to virtual function and non-virtual function. So what does this tell us? There is some slight overhead of using virtual functions, but for short and small virtual function, it is measurable, but for long and slow, it's almost invisible. So the results don't look that bad. But the question is it all? Is there something else to virtual functions? And the answer is yes, of course, yes. So we move on to the next important building block of virtual functions, and these are vector of pointers. So to activate virtual function mechanism, you need to access the object through a pointer or a reference. So if you're accessing an object through a pointer or a reference, the object itself needs to be allocated on the heap using new, using malloc, or using smart pointers, but you will get the place for the object on the heap. Now the problem with heap accesses is that the accessing objects on the heap can be really, really slow. Let me explain why. So we have here std vector of base class, and it's pointing to children classes. So we have child class 1, child class 2, and child class 3. Now, this is what I call the optimal layout. So why is it the optimal layout? Because the neighboring pointers point to neighboring memory addresses. So imagine these are neighboring memory addresses. Now we have something else here down. It's called the non-optimal layout. We have the neighboring pointers do not point to the neighboring memory addresses. So it looks somehow random here. So the question is, why is this important? So the reason why this optimal layout is better than the non-optimal layout is that while you're iterating through this vector of pointers in order to do some kind of processing, with the optimal layout, you will exhibit a much higher data cache hit rate. And high data cache hit rate corresponds to better software performance. If the objects if we are accessing an array of objects and the objects are neighbors in memory, so we are accessing them one after another, we can expect performance improvements. If the objects are not neighbors in memory, so if the CPU needs to jump around memory accessing objects, we can expect slowdowns. So in our case, if we have vector of pointers, and if the pointers are not pointing to the neighboring elements on the heap, we can expect data cache misses, and this will influence performance. Now, when you have your program and you're allocated a vector of pointers, and now you're allocating objects for the pointers to point to. So imagine you have a vector of 1 million pointers, and you will have 1 million calls to the malloc or to you. We have 1 million allocations on the heap. There is no guarantee that the neighboring pointers in the array will point to the neighboring objects in memory. And as the program becomes bigger and more complex, there is less and less chance that this will happen. So the memory allocator will try to reuse the old freed memory chunks. And in that case, you might end up with in a situation where you have pointers in the array not pointing to the neighboring memory addresses. So if you look at it like that, vector of objects is much better for the performance compared to the vector of pointers, because vector of objects doesn't suffer from data cache misses. When you're iterating a vector of objects, you're iterating neighboring memory addresses, and this is good for performance. Now, the problem with vector of objects is that the vector of objects does not allow polymorphism and virtual functions. So let's do some experiments. We have a vector of object that contains 20 million objects. We have another vector of pointers with also 20 million pointers, and pointer at location I points to the object at location I. So we have two arrays. One is the array of pointers, another one is the array of objects. Pointer at location I points to the object at location I. So we have a perfect ordering. Neighboring pointers point to the neighboring objects. Now we measure the time needed to iterate through 20 million objects by following the pointers in the vector of pointers. So we are iterating the vector of pointers, and we are the referencing pointers. Now this is our original experiment. Now we're doing something to what we want to see, what happens if we shuffle around a bit vector of pointers. So the experiment has certain number of instances, a certain number of iterations. So let's say it has 20 iterations. And in each iteration, we shuffle part of the pointer array. And we measure the runtime needed to traverse the pointer array as a function of number of shuffles. So one shuffle means to swap pointer at position 0 with pointer in some random position. Okay. So this is a diagram which says how swapping of pointers in the array influences the speed of access. So we have here On the left side, we have the runtime, and on the x-axis, we have the number of swapped pointers. So remember, we have 20 million objects in our array, and we measure runtime for virtual function and runtime for non-virtual function. So what happens? You see that when the number of swap pointer is small, let's say up to 256k pointers, so this corresponds to about 5% of the array size, the runtime is mostly low, it's about 200 milliseconds. But as the number of swapped element grows, the runtime gets worse and exponentially worse. So you see that when we swapped most of the pointers array, we get to 1.5 seconds. So 1.5 seconds, originally it was 200 milliseconds, so it's about 7 or 8 times slower. So this is all related to pointer swapping. And we observe this effect both for virtual and non-virtual functions. So what's the conclusion? The conclusion is that the memory layout is very important for program performance. So as you have seen in our case, the worst case is 7.5 times slower. Now the slowdown is not related to virtual functions in themselves. The slowdown is related to the memory layout, and that is why we see the same problem with virtual functions and non-virtual functions. But the reason why you actually want to use vector of pointers is to achieve polymorphism. If you don't need polymorphism, you don't need vector of pointers. So you will use vector of objects. Now, this creates problem because bad memory layout leads to bad performance. So what are the alternatives to vector of pointers? So there are several of them. One is to use STD variant with STD visitor. So you use, instead of using array of pointers, you use array of STD variants, and you use STD visitor to achieve polymorphism. It's not a nice way to do it, but it's possible to do it if performance is important, and these two classes are available in C++ standard. So the second thing to do is to use polymorphic vector. This is something that I was playing around. Polymorphic vector is a container similar to array, which uses virtual dispatching but doesn't use pointers. So if you're interested in this, I suggest you Google polymorphic vector. And the third alternative is to use per type vector. So imagine you have 3 classes, let's say 4 classes in our case. So there we had a brass, wind, and 2 more. So you can have per type vector, one vector to store brass, one vector to store wind, and so on. So all the objects in the vector are the same, so it's not a vector of pointers, it's a vector of object. It is very useful, it is much faster than vector of pointers. It's not heap heavy, it's very useful if you don't need a specific ordering in the vector. So feel free to use this if you don't need a specific ordering in the vector. But if you do, this thing is not possible to work. Okay, moving on. So the next difference in performance between virtual and non-virtual functions come from compiler optimization. So what happens is that the compiler knows the address of the non-virtual function at compile time. What this means is that the compiler can inline the non-virtual function and it can avoid the function call. Now what happens is that inlining saves a few instructions on the function call, but that's not the whole story. When the compiler inlines the function, it can perform additional compiler optimizations because when the code is inlined, the compiler has a better overview of how that code fits into the overall picture. So for example, when the compiler has inlined a function, it can figure out that some code inside the function is loop invariant and can move it outside of the loop. Or for example, it can use special instructions of the CPU called vector instructions that can process more than one piece of data at the same time. For example, it can use vectorization to process 4 integers in one instruction. And this can typically increase speed from 2 to 6 times. But this is all possible if the compiler can inline the function. If it cannot, then these compiler optimizations are not possible. So here, have a look at this example. We have this function called mySQRT. So it says something like this. If the bug is set and a is less than 0, then print something on the error console and return the square root of a. Now we have this is my loop, and this loop is iterating over the in and out vectors, and it says my square root of in out of I equals my square root of in of I. So imagine this thing is not inlined. So there is for each element of in there is a call to mySQRT. So what happens if the compiler can inline this code? Let's see. Now this optimization is called loop unswitching. So the compiler inlines this code into this loop. So it copies this body into this loop. And it figures out that this debug is actually loop invariant. It doesn't change its value. So what it can do, it can actually create two versions of this loop. One for the case where the bug is true, and the other one for the case where the bug is false. So if we have the bug is true, then we have this check, and we have this output in case the value is negative. But in case the bug is not set, then the compiler can generate this simple version without any ifs, checks, outputs, and so on. And the compiler can actually vectorize this loop. So if the bug is false, the compiler will execute this loop, which can be much faster. The compiler cannot vectorize this loop here because it cannot vectorize calls to the outputting stuff on the screen. Okay, so this explains how what happens when the compiler inline. So the inlining enabled vectorization. So with inlining with loop and switching enable vectorization. Okay, now we are going to do an experiment and measure the influence of compiler optimizations. So we have here a class called object, and we have here two functions. One is called isVisible, and the other one is called getID3. The isVisible just returns m is visible, and the getID3 returns MID. MID is this, plus moffset, and moffset is a static. It's a stat common to all classes, static member of this class. So here is our test loop. The test loop iterates array of classes, and it gets an object. So this is getting an object from the array. And then it checks if object is visible, that count plus equals O of getID of 3. Okay, so this is our test loop. So we have two calls to two functions. One is visible and the other one is getID 3. So what we are doing here is that we are measuring the inlining, the influence of inlining. So these functions are not virtual. So these are non-virtual functions. So we are measuring the runtime between inline version and non-inline version. What happens is that the inline version takes 136 milliseconds and non-inline version takes 242 milliseconds. Now, part of the reason is the price of the call. So the call and return instructions. But the other, much higher price comes from a much higher reason why this is almost 2 times slower, is that the compiler with inlining of isVisible and inlining of getID3 could actually perform additional compiler optimizations. Okay, so with virtual functions, you have a problem that virtual functions inhibit compiler optimization because the compiler cannot inline virtual functions. It needs to look up their address at runtime. So how do you deal with this? The solution is called type-based processing. First is you don't mix types. Each type has its own container and its own loop. So the compiler can inline small functions and perform various compiler optimizations. So this is already implemented as part of Boost in Boost base collection. So this approach works if the objects in the vector don't need to be sorted. If you need to keep some kind of sorting in the vector, then type-based processing won't work for you. Now, the problem with compiler optimizations is that the compiler optimization that happen because of inlining are very case dependent. Some code profits a lot from compiler optimization, from inlining and additional compiler optimization. Other code doesn't profit at all. In principle, smaller functions benefit more, but this is, let's say, rule of thumb, and it doesn't work all the times. Okay. Moving on to the next. The next thing is called jump destination guessing. So what is the jump destination guessing? Now, to speed up computation, modern CPUs do a lot of guessing. The technical term for this guessing is speculative execution. So what happens in the case of virtual functions? The CPU guesses which virtual function will get called, and it will start executing the instructions belonging to the guessed virtual function. So it guesses the virtual function and it starts executing instructions corresponding to the guessed virtual functions. Now, if the guess is correct, this saves time. But if the guess is wrong, the CPU needs to cancel all the effort it has already done and start over. And this costs time. Now, how efficient the compiler is guessing depends on few things. So let's elaborate. So we have an experiment here. We have 3 vectors of 20 million objects. The first vector is sorted by type. So it's A, B, 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 C, 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 D, 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 D. So objects in the first vector are sorted by type. Objects in the second vector are sorted in a predictable fashion. So you see A, B, C, D, A, B, C, D, A, B, C, D, A, B, C, D. And in the third vector, types are random. So there is no particular sorting. So these are the types, and these are B, CA, CA, CBBA, CBA, for example. Now we measure time needed to call a small virtual functions on the 3 types of vectors. So we have the type 1, type 2, and type 3. So if they're sorted by type, or they're sorted in round-robin fashion, in a predictable fashion, the runtime is about a bit less than 200 milliseconds. But if the types are not sorted, so then the runtime is almost 500 milliseconds. So they're almost 2.5 times slower. So this is a very, very interesting observation. So what happened here? When the types are sorted in a predictable manner, the CPU can very successfully predict the address of the virtual function, and it will go there and start execute that code, and this will lead to performance improvement because its guesses will always be correct. Now, if types in the array appear randomly, the CPU cannot guess successfully, and some CPU cycles are lost. Now, the solution for this, again, is type-based processing, as we already explained. But again, type-based processing is not always usable. Now, this effect is mostly pronounced with short virtual functions. With long virtual functions, this effect is much, much less visible. Okay, so this finishes the talk about jump destination guessing. Now, the next reason why virtual functions are different in performance compared to non-virtual functions is called instruction cache evictions. Okay, so what are instruction cache evictions? Now, modern CPUs rely on getting to know the instructions they're executing. So if the CPU has already executed recently the instructions, some instructions, and it is now executing again. It knows those instructions better. This code is called the hot code. Why is it called the hot code? Well, the instructions that the CPU is now executing are already in the instruction cache, so access to them is faster. The branch predictors, so related to the jump destination guessing, the branch predictors in the CPU know the outcomes of most branches. The jump predictors know the outcomes of jumps. So this is a hot code. The CPU knows a lot of statistics about it and can make more informed decisions about what to do with this code. Now the CPU is faster when it is executing hot code compared to executing cold code. So why is this important for us? The CPU's memory is limited. So the code that is currently hot will eventually become cold if the CPU doesn't touch it for some time. Now we have the problem here that if we have virtual function, and we have especially large virtual functions where each object has a different implementation of the virtual function, that means the CPU is switching from one implementation to another implementation to another implementation, and most of the times it is executing cold code. Okay. And when you're executing cold code, your code will be slower. Okay. Sorry. So we want to measure the effect of instruction cache evictions and running cold code. And this is the hardest part because it depends on many factors. First, it depends on number of different virtual function implementations. So if you have 100 objects, 100 types, and you have 100 virtual functions, for each type has its own implementation, so nothing is shared, you will get slower code. So the bigger the number of implementations, the slower the code. The second thing that influences is the number of executed instructions in the virtual function. So we have a virtual function and a lot of instructions that the CPU executes inside the virtual function. This will mean slower the code. So you should not confuse the size of the virtual functions and the size of the virtual function and the number of the executed instructions. Why? Because sometimes the virtual function can be really large, but actually only a fraction of its instructions is executed. So from the CPU perspective, this is a small function. Also, one thing that influences this is how sorted are the objects in the container. When I mean sorted by type. So the best case happens when they're sorted by type, like this: A, B, 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 C, D, D, D. The worst case is when they're sorted by type in a round-robin fashion. So A, B, C, D, A, B, C, D, A, B, C, D. I think you get my point. Okay, so in the best case, the CPU will execute the virtual function for A, then it will move to virtual function for B, then it will move to virtual function for C, and so on. In the case when they're executed in a round-robin fashion, it will execute virtual function A, then B, then C, then D, then again A. And when it starts executing the virtual functions for A, the CPU has already executed the virtual function for A, but it was a long time ago, and this is now again cold code. So we have an experiment here. We have 4 classes called rectangle, circle, line, and monster. And we have 4 implementations of long virtual function. The long virtual function consists of a for loop with a large if, else block inside it. So we have a for loop with a large if, else block inside it. For measurement, we use 2 vectors. Each vector has 20 million objects. One is the vector where elements of the vector are sorted by type, like this. And the second vector is the vector where elements of the vector are sorted by type, but in a round-robin fashion. So it's A, B, C, D, A, B, C, D, A, B, C, D. Now, we change the size of the function by changing the number of comparisons in the large if, else block. And then we compare the time we need to iterate the 2 vectors. So let's analyze this graph. On the x-axis, you have the number of if clauses in the function. So they go from 0 to 100. 0 corresponds to a small virtual function and 100 to a large virtual function. Here on the left side, we have the ratio, so runtime sorted divided by runtime round robin. So we have a ratio between runtime ratio between the sorted version and round robin version. So we will see when the number of comparison is 1, then the ratio is about 1. But as the virtual function grows, because the number of if clauses in the function grows, this ratio becomes smaller and smaller. And when there are about 40 if clauses inside the for loop, then the round robin runtime is 0.6. Sorry, the sorted runtime is 0.6 times the round robin runtime. So it's the sorted version is almost 2 times faster. In the worst case, the same function took 70.5 seconds to execute in the sorted vector and 12.3 seconds to execute in the round robin vector. So this thing is related to the instruction cache evictions and the size of the virtual function. Again, the phenomenon is not related to the virtual function themselves. So if you have, for example, if you're accessing through vector of, if you have a vector of functions and you're calling vector of functions and the functions are pointing to the different functions, you will experience a similar phenomenon. Now, when this actually happens most of the times is when we have large virtual functions on mixed type unsorted vectors with many derived types. So this is where this actually happens. Okay, this ends our talk for today. So before the end, a short conclusion. So the virtual functions themselves do not incur too much additional cost. So for small virtual functions, about 20%. For large virtual functions, it's almost invisible. But what actually determines their performance is the environment where they run. So what hardware craves is predictability. You have same type, same function, neighboring virtual address. If you have that, you will have good performance. And virtual function, because of the flexibility they offer, they allow you different types, different implementations, so different functions, and with pointers you have non-neighboring virtual addresses. So when you have predictability, hardware run at its fastest, but it's not easy to achieve this with casual usage of virtual functions. So this has been a longer problem in game development, and for these precise reasons, they use different paradigm called, instead of object-oriented programming, called data-oriented design. Now, one of its major parts of data-oriented design is type-based processing. So each vector holds only one type. So this eliminates all the problems related to the virtual functions that we have here. But this approach is applicable in game development. It's not applicable everywhere. So a few ideas on how to mitigate the problems with virtual functions. The number one factor that is responsible for bad performance are data cache misses. So if you avoid vector of pointers, you will be fine. Other factors also play their role, but to a lesser extent. If you design your software carefully, you can reap most benefits of virtual functions without incurring too much additional cost. So a few ideas how to fix your code with virtual functions. Bear in mind, arrangement of objects in memory is very important. So you want to have neighboring objects, neighboring pointers pointing to the neighboring objects. You want to try to make small functions non-virtual. So most overhead of virtual functions come from small functions because they cost more to call than to execute. You want to keep objects in the vector sorted by type. So this is also very important. If possible, it will affect virtual function performance. So this is the end of this talk. thank you for paying attention. If you're interested in C software performance, you can subscribe to my blog, where I write about this stuff a lot. And here are the links. If your program is slow and you need help, you can contact me directly. So this is my email address, and this is also the address where you can find more information. So any questions? So this is the pre-recorded talk, and the questions will be held live. Thank you very much. Okay, in the summary slide, is hot path mean that the vector elements are in random order? No, hot path in performance engineering, hot path is the code that is actually executed by the CPU and takes a lot of time. So we call this hot code, or the code is on the hot path. So this is what's meant under hot path, and you'll hear this term a lot. There's also as Jonathan asked, there are some older questions asked before the talk finish. Yes, there are, but I mostly answered those, so you will see them. You will see them as answered in the question and answer box. So anonymous. So in non-polymorphic use of inheritance, that is using derived classes without heap allocation point access, generally not as much of a concern. Yes, as you've seen, like the biggest slowdown comes from pointers, so it's not related to virtual functions. So if you take if you pay attention to that and just avoid pointers and share pointers and calls to malloc and free, you'll be fine. Okay, tools you normally use for measuring performance. So what are the tools that I use for measuring performance? Normally I use, so there are many tools you use performance. So the basic one is multi-time on Linux. So I work mostly with Linux. The basic one is multi-time, and it will execute your program several times, and it will print out the it will run a program several times, and it will print statistics about runtime, standard deviation, such numbers. Now this is like the basic. Then if you want to read hardware counters like instruction cache misses, branch prediction misses, you will use perf on Linux. Alternative is Intel's VTune profiler, which is really good. The Intel's VTune profiler does this top-down analysis where it can tell you what is the reason that makes the most. Why is your hot loop or hot code slow, in the sense that where is the hardware bottleneck in memory, in CPU, in speculation, and so on. So VTune is really good for this hardware efficiency stuff. And I use those tools a lot. And also there is this tool called Liquid. Liquid is like also performance counter library. It's free, it's available online, it works on many systems. It will measure runtime for a segment of code. You segregate the segment of code with this liquid marker start and liquid marker stop, and in between it will give you different information about that code that you marked. Okay, did I see that you come from an embedded background? If so, do you ever use C++ style inheritance in your design, or do you use alternatives? So it really depends on the project. In my project, we use C++ style inheritance, but normally, if you, embedded is the word embedded now means too much things. Like earlier, it was like a small microcontroller with 4 kilobytes of RAM is embedded, but it's also a chip which ARM64 with 4 gigabytes of memory is also embedded. So it actually really depends on the system. Okay, is hot code different to code on a hot code? Is the code on the hot path. The hot means it executes a lot, so it's taking time. It's spending CPU cycles. Hot code was so I thought you mentioned that hot code was code that was executed recently. So generally means that hot code is the code. It doesn't need to be executed recently. It's only the code the CPU spends a lot of time executing. Now, the term for that would be like recently executed code, the code that CPU knows still knows, has some statistic about its runtime, so they can predict and run it faster. Okay. Similarly, is polymorphic without virtual function also a PB on performance, variant static polymorphism through templates? Polymorphic without virtual functions. So please. So static polymorphism. So the compile time polymorphism using templates is actually one of the techniques that you can use to speed up codes that are suffering because of the dynamic polymorphism, and templates are actually used when you're converting a runtime parameter to static time compile time parameter. The compiler can actually do much more compiler optimizations and produce faster code, and this is often done for parameterized code. Is that CRTP? I have no idea what that means. Okay, can you please repeat the performance tools on Linux? So multi-time, Intel's vTune profiler, perf is the built-in profiler in Linux. It's really good. Liquid, LIKWID, so it's available on GitHub. So these are the tools I use most often. Okay. What's your opinion on object-oriented paradigm in general? Do you have preferences on when it's used versus using a different design paradigm? I don't have opinion because I mostly deal with performance, and it would be unfair to talk bad about object-oriented paradigm. Object-oriented paradigm, from the performance standpoint, it's not the best, but the performance is only one aspect of software development. Also, other important aspects are code maintainability, easy to read, and so on. So, and these are also important, and many times more important than performance. So my opinion about OOP is quite neutral. So, except for the virtual function address not known at compile time, there are not all the issues you talked about in the context of video game development. So the video game development use this data-oriented paradigm, data-oriented design, or they also call it entity component system. There is actually one really good book about it because it gives you a really nice idea how you can develop things a bit differently. It's called Data Oriented Design by, I think it's Richard Fabian. I'm not 100% sure. So the game developers, they have this problem that they need high performance software. So the games must run fast. But they also need the flexibility. So the game should be flexible and easy to write. So when they are programming using the standard object-oriented paradigm, but they have a really low hardware efficiency. So a lot of time is wasted because the program is not hardware efficient enough. Now somebody sat and thought about it and did measurements and did things like that. And finally, they came that this data-oriented paradigm is much more hardware-friendly, and that's why they're using it. Although the data-oriented paradigm is quite different from object-oriented paradigm, and it's actually, in my opinion, it's really dedicated to developing games, and I'm not sure in what sense it can be applied everywhere. So this is something that a guy or a girl who has a lot of background in data-oriented design can answer. Okay, so I think that's it. There are no more questions. Thank you very much, everyone, for attending, and have a good day. Enjoy the CppCon. All the best. Bye.